Yep, all set. Thank you.
Okay, perfect. So now I will talk a bit more about coupling with waves. So more focused on ocean wave coupling, but also a bit on atmosphere wave coupling. So first, I will talk a bit more about waves because it's kind of a bit different the way we understand and model waves than what we do in the ocean. So waves are what we are all these kind of waves can be described. So you can describe them from the wavelength or the frequency or their period, for example. And we go from capillary waves towards gravity waves and longer wave period like tsunamis, tides, and stuff like that. And today I will mainly talk about wind waves. So these are the waves generated by winds. And they can go from capillary waves that are a few centimeters long towards typical wind waves that are like about less than 30 seconds of period. Infragravity waves that are waves generated both by wind and wave-wave interaction that can have a slightly longer periods. And there are also inertial gravity waves, and I won't talk so much about that, but it's typically Kelvin and Poincaré waves that are influenced both by wind and the Coriolis force. So when you think about waves, you think at these nice crests that you can see at the beach and that are perfect for surfing, but also all the small waves that we can have riding on these larger waves. And so on the right-hand side, you have like this superposition, let's say, of different wave system, which is something that we will use to describe the waves, because as we can see, waves can have very different scales, and there are obviously of very small scales, and this is very difficult to model. So what we usually do is to use a spectral approach to describe waves that is considering the sea state as a superposition of various elementary wave described like sinusoidal waves. So this is what is represented on the right-hand side. And then we can describe this full sea state and combination of waves with a wave spectrum. So there is an example of a wave spectrum at the bottom that described the surface elevation variance across scales. So as a function of, for example, frequency or period, or even space. And we can have different peaks in this spectrum representing the wind sea, the swell, the infragravity waves, or even the tide. And this spectrum is related to the significant wave height by this relation, which is significant wave height equal 4 times the square of the integral of the spectrum. So this is a way to really statistically represent the wave system, and which is quite useful at large scales. So now just to give a few words on the wave life cycle, let's say, so generation, propagation, and dissipation. Wave derives their energy from the wind, and they release this energy into the ocean through turbulence and breaking, for example. And so about 70% of the wind stress is directly transmitted to the waves and then used partially for wave growth. And part of the momentum then is then communicated to the ocean circulation through breaking. In addition to this generation by the wind and the dissipation, we have also nonlinear interaction that can occur between different wave systems into the waves. So to give you an idea of the state of the art of what we know on these 3 topics, so propagation, it's quite well known. There were a lot of works on that in the 18th and 19th centuries. And so this is something that we and dissipation, it's much more parameterized, and it's still very active research topics because it's quite complex to represent, and notably because of the multi-scale nature of real ocean waves. So different influence between waves and between scales. So just a word about generation. So as I said, it's still state of the art because there are several theories that were made, but none of them fully explains how we can generate waves from a surface at rest. So to simplify here, there is a small sketch explaining how we can grow a wave from a surface that is already with some small waves. The fact is, if you put an observer, for example, here on one side of the wave, what happened is here the wind is accelerating, and this induces an overpressure of the waves, which make them descend. And if you have an observer here, you can imagine that as the wave is moving, the observer first was at the crest, and now it's descending toward the shore. So we have an increase in the descent motion. So we will increase this motion, and the other side of the wave is the same. So if we have an observer over there, it was at the bottom, and now it's going towards the crest. And as we can see, we have a depression here, and so it's increased the motion of the wave as ascending. So this is a way that we can grow a wave from an already existing little wave. This can be translated into a parameterization of the wave growth, and here there is an example of formulation that was proposed, and you can see that it depends obviously on the density of the air and the water, but also on the angle between the wave and the wind. So this term is positive when the waves travel in the wind direction. It's negative when the waves travel in opposite to the direction of the wind, and it's zero for the waves traveling in direction normal to the wind. So the transfer from the atmosphere towards the waves exists only if the phase speed of the wave is lower than the wind. Otherwise, if the waves travel faster than the wind, then the waves can give back energy towards the wind. So this is quite important. It's something that we use a lot. It's what we name the wave age, which is this ratio between the phase speed of the waves and the wind speed. And this is something that we use to consider what kind of sea state we are dealing with. So if the waves are young, so they have just been generated by the wind, they are short and they are going quite slowly, and so the phase speed is lower than the wind. And when they are getting more mature, so older waves, then the wave age is greater, and we have a phase speed of the wave that can be greater than the wind. And if we look in general in nature for a fully developed sea state, we can see that dominant waves are propagating 20% faster than the wind. So it's just to give you an idea. So how these waves propagate, actually, so to study and model the wave propagation, we can use the linear wave theory first. And this linear wave theory is based on a simplification of the Navier-Stokes equation, following a lot of hypotheses. So here you have the various hypotheses that are used, that are listed. So incompressible water, no viscous effect, irrotational fluid, neglecting nonlinear terms. The Coriolis force is considered negligible. There is no mean current, and waves are of small amplitude compared to their wavelength. And we have a flat bottom, non-permeable, and constant depth seabed. So from this, considering Navier-Stokes and all these hypotheses, we can derive the typical wave equation that is written on the right. And from that, we can have a classical linear dispersion relationship. This is characterizing the wave potential, which is the potentials of the velocities associated to waves. And it's very useful to describe the wave propagation. So now, with this framework, if we look at the general view of the dispersion relation, we can have an associated phase velocity and group velocity. So the phase velocity is the velocity of evolution of the crest of the waves, and the group velocity is the evolution of the energy of the waves. And if we look at the approximation of this equation in deep and shallow water, you can see that, for example, in deep water, the phase velocity of the waves, so in the middle, depends on the wave number. So you can see that depending on the wave number and then on their wavelengths, the waves are not traveling at the same speed. So it's what we call waves are dispersive. In shallow water, it's not the same anymore. you can see that the phase speed of the waves is only depending on the depth. So for a given depth, all waves are traveling at the same velocity. And this is quite important because it really changes the behavior of the wave system. Then, if we want to look at the motion induced by waves, it's orbital, what we name orbital motions. So for that, we can deduce the velocities associated to waves from this potential and from the wave equation. So here I won't go into details in the equation, but something that is interesting to note also is that if we look at deep water and shallow water approximation of these velocities, in deep water, both the horizontal and vertical velocities depends on the exponential of the depth, so they decrease exponentially with depth. While if we look at shallow waters, what happens is that we have different expression, and now the vertical velocities decrease much faster than the horizontal velocities. And now I put some sketch. So these orbital motion here in deep water are quite circular in the linear wave theory. And when we go to shallow water depth, we have these elliptical shapes with an increased velocity in the horizontal compared to the decrease that we have in the vertical. So this is in the linear theory, and we will see that it's quite different when coming to wave current interaction. These waves, they also induce some energy in the ocean. So there is a potential energy associated to the change in the surface elevation. And there is also a kinetic energy associated to the velocity of the waves. And if we sum both of these energies, we have the total energy induced by waves that is dependent on the wave amplitude. And when this is the formulation on the left that is given for one component of the waves, but we can extend that to a spectrum, taking into account the amplitude of each wave component. Then, what happens when waves propagate across the Earth? So waves can propagate really far from their generation area. And due to that, we definitely need to take into account the Earth's sphericity to understand their propagation. And the propagation on the shortest path on the sphere, which are the grid circles. And as I said, in deep water, waves are dispersive, so different wave components won't travel at the same speed. So that's why what is illustrated on the right-hand side plot, the shorter wave will travel slower than the longer waves, which travels faster, and then that reach a given position earlier. So here you have an example of how you can compute the time at which each wave system will arrive at a given position, depending on the radius of the Earth, the spherical distance, and the time at which they were generated. So it's important to remember, so different wave components don't travel the same speed. So then there is also dispersion of the waves associated to this different velocity in propagation, but also we have some impact on the height of the waves. So due to this dispersion, because as we have a dispersion of the different wave system, the height will also be different because part of the height is associated to each component of the waves. And so we can compute also the dissipation, the decrease in height over a given distance depending on this dispersion. And this is neglecting even the part of dissipation actually due to wave breaking and interaction with islands or other features. Now, so obviously, besides propagating, wave can dissipate by different phenomena, interaction with different other stuff, but also just typically breaking. So waves, if the crest starts being faster than the rest of the waves, obviously they break. So there were some works from Misch that showed that the maximum steepness of regular wave is given by a given criterion. and that we can evaluate breaking from that. And there are different kinds of breakings that are illustrated on the right-hand side. So there are microbreakers. So it's really, really small breaking that are on a scale that surface tension are affecting them. So there are no air bubbles, but they can be diagnosed from very high resolution temperature measurement, for example, with increase in temperature at one side of the waves. Then there are two kinds of more common breakings that you can observe. The spilling breaking, which is when the crests become unstable and there is a generation of foam and turbulence at the top of the wave. And the typical plunging breaking, which is when the crest instability and speed is so great, then you have this nice tube that are nice for surfing and for beautiful pictures. So this dissipation needs in models to be parameterized also, because it's, you can imagine it's quite difficult to evaluate. And so we evaluate a rate of energy dissipated per unit of ocean surface by this breaking. And this depends on the dissipation rate, so this epsilon here, a breaking probability and a saturation spectrum. So this is a way that we parameterize dissipation due to breaking in wave models. Then waves can also have nonlinear interactions, as I said, and this is due to the wave-wave interaction. So depending on the various frequency of the different wave systems that compose the wave spectrum, if some conditions are met, so some combination of frequency or wave number between these wave system are met, so we can have triad interaction or quadruplet interactions, then we can have a transfer of energy within the spectrum. So there is no loss of energy. It is just that within the spectrum, we have a transfer of energy from one component to another. And for example, in the case of wave growth, we have first small waves that are generated by the winds, and with wave-wave interaction, the energy will be transferred towards longer waves. So now that we have said some words about waves, let's talk about why we want to couple them with an ocean model. So here is a sketch that shows different processes that are interesting and relevant for wave-ocean coupling. So wave-ocean coupling, there is interaction for the circulation and mixing, obviously. There is also an importance of waves for RC fluxes. In the nearshore circulation and land sea exchange, we will see that waves are very important. They can also interact with the sea ice and have some specific effect on the sea ice. And they also interact with the ocean crust, and they can be recorded because they induce microseisms, and so it's recordable with typically seism systems. And waves also are very useful for a lot of applications. For example, for remote sensing, actually, when we use all the radar technology, we can measure, obviously, significant wave height, but also currents or winds, for example, thanks to waves. They are also important for engineering, of course, design of offshore and nearshore structures, and they are important for maritime transport, and they have impact also on the drift of objects and pollutants in the ocean, and as they induce all these kind of features that we have seen before, they have impact on the biology of the ocean. So now let's go first on what is the impact for waves when they interact with the ocean. So we have seen all these equations of the propagation of waves in the linear theory. And we can see that when waves are on a current that is not uniform, actually, and they have a change in their phase and group velocities. So now the phase velocity is not just the velocity of the waves, but the velocity of the waves plus the current, and similar for the group velocity. And so this changes slightly the frequency of the waves. And so we have different impacts of this change towards waves. So first we have For example, current gradients induce shoaling of the waves. What is shoaling? It's a modification of the amplitude associated to the variation of the group velocity. So here, if we change the group velocity, as we need to have a wave flux conservation, so typically the wave flux is the energy of the waves times the group velocity. So if we want to conserve this energy flux, obviously, if the group velocity change, we need to change the amplitude, as the energy is dependent on the amplitude of the waves. So changing the group velocity, we are changing the amplitude of the waves. Additionally, with the current gradient, as we are changing the phase velocity of the waves, we are changing also the wavelength of the wave. So we have an impact of this current on the wavelength and the amplitude of the waves. These current gradients also induce what we name refraction, which is a change in velocity in a lateral direction, let's say, causing the fact that the waves can turn, actually. So here is a sketch on the right-hand side, and you can see that if the current is not the same for a given wave train somewhere, over a current gradient, we will have a different behavior of the waves. And if you here again take some equations to have this wave flux conservation along a given beam and the beam next that, you can derive the change in amplitude and the change in velocities and then in the way that the waves are turning. So here are some illustrations actually of that. And you can see on the left that you have the significant wave height gradient derived from satellite observation. And underneath, you have the mean geostrophic current vorticity. And you can see that these two maps are very comparable. So definitely, we have strong impact on the currents towards the wave height. And on the right-hand side, it's a zoom on the Agulhas retroflexion current, and you can also see that there is a clear pattern of the significant wave heights that is really strongly correlated with the pattern of the current vorticity. And on the bottom, you can see that if you have data, so the data from altimetry in black, it's a time series of the significant wave heights. And then if you model the wave heights with a wave model, but without accounting for currents, you have the red line, which is similar in, let's say, the general trend, but missing a lot of the high frequency variability of the waves. And now, if you account for current wave interaction in the wave model, you have the blue lines, which is much closer to observations than the red one. So it's quite very important to consider high frequency and high resolution variability of the wave. Now, if we look at the impact of this wave current interaction on the ocean side this time, here you have the orbital motion of the waves that are with no underlying currents, as we saw earlier in deep ocean. They have its circular motion according to the linear wave theory. But now, if we have underlying currents, the orbitals are not closed anymore. And there is a drift that results from this unclosure of the orbital motion. And if we are at equilibrium, this drift will be compensated by an integrated transport over the vertical, which is named the Stokes-Coriolis transport. But this is true only at equilibrium state, and it's not necessarily reached at the moment waves are just being generated by the wind. So when waves are young, at this time, we have a drift that is significant due to these orbital motions of the waves. And here you have an illustration on the right of this Stokes drift, depending on the stage of development of the waves. For long swells, so it's in dashed, you can see that the drift is small because there is the wave is well established and the transport that balance the drift is well established too. But going to short swell and then young wind sea, you can see that the drift is much more significant. And this has a strong implication, actually, notably for tracer advection and particle advection. And on the bottom, you have an illustration of the sargassum coverage in the Atlantic Ocean, and its difference of coverage between a simulation accounting for waves or not. And so you can see that there is a stronger impact on such a particular advection over the ocean. Then the waves also induce mixing, as we said. And here you have a profile of the turbulent kinetic energy injection through wave breaking and wave turbulence interaction. So on the left, the profile is linearly with depth, and the second profile is the same, but in a logarithmic scale, just to show more what is happening close to the surface. And in dashed line, it's a Stokes drift, and then it's the part of turbulent energy and braking that is induced by waves. And on the right-hand side, you have maps of this, the 1 meter depth turbulent kinetic energy in the NEMO model, and the difference actually between coupled with waves and uncoupled, so no impact of waves in the ocean model for 2 seasons. And you can see that there is obviously strong impact of turbulent kinetic energy, especially in the winter hemisphere, and where we have strong winds in general at these seasons. And if we look at the impact of that, for example, on the mixed layer depth, it's given here. So this is a probability density function of the mixed layer depth. So in black, it's with Argo data, and the various colored lines are the model with including different terms associated to coupling with waves. So we can include the Stokes drift, of course, we can include the turbulent kinetic energy change, but also the change in the wind stress. We will see that a bit later, but the waves will change the wind stress, and the change in the currents, obviously. So we can see that when we take into account all of the wave-induced interaction, which is the red line, it's much closer to observation than if we don't, so which was the blue line when we include nothing. Finally, another circulation that is induced by waves is the Langmuir circulation. So this is a circulation associated of small rolls, let's say, associated to the fact that the mean flow interact with the wave average flow. So the Stokes drift associated to waves will stretch the velocities close to the surface and also in a special direction, let's say. And this stretching will produce vorticity in the upper ocean, which is balanced by a downward diffusion. And this creates these cells and these small rolls of upwelling and downwellings in space. So this was for the open ocean, but there are also a lot of interesting processes about waves in the coastal and nearshore area. So the different processes that we saw with current interaction in the deep ocean was shoaling and refraction, for example, also occur in the coastal area. And in addition to that, we have also diffraction, reflection, a lot of nonlinear interaction, and some dissipation associated to the bathymetry. So I will go a bit further into these different processes. So shoaling, as we said earlier, it's associated, so it's a change in amplitude of the waves associated to the fact that the group velocity is changing. So if you remember the linear wave equation and the dispersion relation, we have something in deep water that was associated to the wave component, and then something in shallow water that was associated to the depth. And so the group velocity is changing, and to compensate this changing group velocity to conserve the wave energy flux, which is E times CG, we have a change in amplitude. So this is the typical shoaling effect. Then we have refraction, so similar to the interaction with currents. At the moment that waves are propagating towards the coast, they velocity is also changing depending on the depth. And so going to smaller depths, the waves are traveling slower, and this will make their direction change according to this conservation of energy flux along a given beam. So the little sketch really illustrates that, and this induces a change in the direction of the waves, the main direction of the waves, and a change in the amplitude also of the waves. Then we have the effect of diffraction. Now, this is a bit specific. So at the moment that we have a strong wave train incident to a coast and it reaches an obstacle, given obstacle, there is a sudden change in the wave amplitude behind the obstacle. And in this case, this strong change in amplitude due to the obstacle makes the wave not linear anymore. And so there is a change also in phase and group velocities that is associated at that moment to the change in amplitude of the waves. And is illustrated, given by these relations. And so as the phase and group velocity changes, the waves are turning. So this is a typical diffraction effect. Then we have reflection. So this occurs when the variation of the water depth, or it can be the current, but it's less often, let's say, are significant compared to the change in the wavelength. So at that moment, we can have some reflection of the waves. And the magnitude of this reflection is generally characterized depending on the slope of the bottom. So a strong slope will generally induce more reflection than a small slope. And depending on the wave period, of course. And Mich did a lot of work around waves, and you will see his name often in this presentation, but typically he gives some parametrization of this reflection depending on the beta, which is the bottom slope here, and the wave height and the wave period. And more recently, we had also new parametrization, like the parametrization given by Arduin and Roland in 2012, that is, for example, used in the wave wash 3 model. So different parameterization can exist. But this requires also, in general, to know the slope of the bottom, which at a global scale, it's not always easy to have. Finally, we have nonlinearities, also like wave asymmetries, typically in the nearshore. So as waves shoal, as we have seen, we have a decrease in the group velocity, an increase in the wave height, but also decrease in phase velocity and thus a decrease in the wavelength. And the steepness of the wave, which is the ratio between the wave height and the wavelength, does increase. And so we have from going from a more sinusoidal shape, let's say, we go towards a more and more asymmetric shape of the waves. And this front-back asymmetry is associated to a strong acceleration of the flow under the crest, which will be quite important, for example, for sediment transport. So this is something to consider also induce some braking at some point. There are also what I talked slightly about that at the beginning, infragravity waves. So these are low frequency waves that are associated to the presence of wave groups. Actually, they are formed by the fact that we have wave-wave interaction and wave groups interaction. And so what is a picture on the sketch on the bottom is that if you have different wave groups with slightly different frequencies, at some point you can have interaction between these frequencies and you can create these wave groups that in average change the elevation of the sea level. And that's why when you are at the beach, here on the right, you have the time going toward the right, and then the motion of the waves at the beach, so the wet part of the beach versus dry part. And so this is a swash motion, what we name the swash motion, so the motion of the waves towards the beach. And we can see that we have this, regular motion back and forth, but also a change sometimes with waves going upper at some point. And this is due to these wave groups and infragravity waves. Finally, we have dissipation. So we have talked about breaking a bit earlier, but this dissipation need to be parameterized in models. So we have this breaking due to steepness in the deep ocean of the waves, but we have also depth-induced breaking, so that should be parameterized, and also bottom friction. So at the moment that the waves are in shallow enough area, they will impact really the bottom, and that can induce some sediment transport. And this bottom friction will also induce some dissipation. So this was the part for the waves change, but now let's look at the wave-driven circulation in the nearshore area. So this is a sketch representing all these processes. So we have the change in the orbital velocities, the fact that the waves are becoming more asymmetric, that they shoal, and the generation of turbulence and braking and the impact of the waves at the bottom and stuff like that. And I will go a bit further into these different processes, but I think that also Rachid tomorrow will talk to you a bit more about that. So at the moment that waves arrive close to the coast, they have impact on the sea level, obviously. So we talked about infragravity waves, so the fact that we have wave groups, and these wave groups will induce some force, and they will generate a change also, as I said, in the average sea level. So this is the first example of impact of these waves. Then we have an impact that is named the wave setup, which is associated to the fact that in the braking zone, wave height rapidly decreases, and the resulting gradient in the radiation stress of waves impose a force that is directed onshore. So this is this blue arrow on the sketch, which is balanced by tilt of the water surface, which is the red line over there, named the setup, so the wave setup. So the fact that waves are breaking induces this increase in the surface elevation at the coast. And there is a third change in water level that we can say that is really what is happening on the beach, which is named the run-up. So this is the difference of the water level depending on the swash, so this back and forth motion of the waves on the beach. But this is not a mean sea level that is changing at this point. So waves also induce different currents. So first we will go to longshore currents. So remember when the wave breaks, we said that it induces a wave setup, so an elevation of the sea level. So this is in the cross-shore direction. But as the waves generally does not arrive just normal to the beach, and if they come with a given angle, there is also a component of the radiation stress which is parallel to the coast, and this is balanced by a longshore drift associated. And you have an example of the impact of such a drift on sediment transport on the picture over there. If you have a typical incidence angle of the waves, you can just transport with this longshore drift some sediments, and you can create this sand tongue, for example, here as pictured. So this is quite important also for sediment transport. And finally, now let's go to the cross-shore circulation that we can have. So we discussed different features before that are, so this is the Stokes drift with these orbitals that are not closed. We have also boundary layer streaming, which is a wave stress on the bottom, which is in the direction of propagation of the waves. We can also have mass transport due to what we called wave roller, which are actually a fraction of the wave energy that is converted to rollers that propagates toward the shoreline before dissipating. And so all this circulation if you look at the little figure on the right, are directed in red towards the coast. And to balance that, there is a current that is the undertow, which is directed in the bottom offshore. Then there is a third effect that is also well known in the coastal area, which is a rip currents. And these currents are due to non-uniform bathymetry. So for example, on the sketch, on the bottom, you can see that if you have some sandbars, you will have onshore flow toward the bar due to breaking, induced breaking, and some vorticity that is created at the edge of the bars that create also an offshore current. And this is typically what is shown on the picture, and it can be shown in a lot of energetic area, coastal area. And it creates a really strong offshore current, which is quite dangerous for swimmers. So now let's move to wave-atmosphere coupling. And you will see that it also can impact the ocean. So typically through the roughness parametrization. So the wind stress over the ocean is computed as a turbulent stress. And this turbulent stress is generally parameterized through a drag coefficient. So the CD in these formulations. This drag coefficient depends on the roughness length, which is associated to the roughness of the surface. And this roughness is associated to the short waves, generally. So what we generally use in atmospheric models is a parametrization of this drag coefficient as a function of wind. So we have an increase of this drag coefficient with wind. But you can imagine at that point that it can also depend on waves and not just wind, as I said, that waves and wind are not all the time in perfect equilibrium, let's say. And when we go to really stronger winds, here, generally, we have also a saturation of the drag coefficient, which is known from observation, but not fully explained, let's say. And even more generally, here is a state-of-the-art of drag parametrization. And you can see that there are numerous formulations existing with very various values, especially at high wind speed. And this is really state-of-the-art, so we still have a lot of work to do on that. And there is not always a consensus on that, even sometimes at moderate wind speed. And if we look at there were numerous studies that said that this difference formulation are associated to the fact that we need to account for waves and the variability of the wave state. And so we should account for example, the wave age. So let's remember this young wave versus older waves. And if we look at this drag coefficient computed, for example, in a wave rescue simulation here, it's all the gray points are the various drag coefficients that we have at the different point of the simulation. And we can see that we have a spread. And if we compute in color the average by wave age category, which is these different colors, we can see that we can indeed have different slope of this drag coefficient depending on the wave age. So definitely we have something to improve there. And when we are coupling wave and atmosphere, we can do that actually. That is taking into account this variability of the drag coefficient depending on the wave age. Then just an illustration of how it can be important, for example, in the case of tropical cyclones. In tropical cyclones, we are on the edge of the distribution, so very, very strong winds. And in a tropical cyclone, we have cyclonic winds that are turning into the cyclone and generating short wind waves. And we have also sometimes another wave system, which is swell, which is actually waves generated before. And we have this composition of young and older waves, let's say, and which is definitely not symmetric around the cyclone. So this creates a stronger asymmetry in the wave field, which is quite important. And Also, depending on the translation of the cyclone, we will have a variability of this wave field. So here is an illustration of an analytical wave model that generates waves under an analytical tropical cyclone. And going towards the bottom, we're increasing the translation speed. And this is actually rays of waves. So you can imagine that when at the beginning the cyclone is stationary, on top we have waves obviously around the cyclone, and that are time to they are leaving the cyclone but slowly on all sides. But when the cyclone is moving faster and faster, you can see that all the waves will be, for example, here only at the back of the cyclone. It really depends on the translation speed. And so here you have an average view of the wave field. So here, significant wave height under a tropical cyclone. So it's an average of a lot of tropical cyclones, depending on the intensity. So this is over the y-axis, and over the x-axis, it's depending on the translation speed. And you can see that in general, the wave height is higher in the right-hand side of the cyclone, in the northern hemisphere. It's the opposite in the southern hemisphere due to the cyclonic rotation of the winds. But that also depends on the translation speed. And when the cyclone is going faster, the wave height will be higher on the front. And this has strong implication for Earth interaction, because if we look now at the drag coefficient, and here it's illustrated through the Charnock coefficient in color, we can see that depending on the intensity and the translation speed of the cyclone, typically the pattern of the Charnock coefficient is completely different. And this is quite important. And this is associated to the fact that we have different wave system and also different wind intensities in the different part of the cyclone. And so this has strong implication on the wind field. This is just the same than before. And then finally, we have also impact on the sea spray. So the ability of the winds to rip out, let's say, droplets from the waves. And this sea spray, so all these droplets will have an impact on different things. First, on the airflow stratification, because water density is heavier than air density, so it impacts the stratification. And there is also a change in the fluxes, so latent heat flux and sensible heat flux associated to the evaporation of these droplets. And this has a strong impact also on the drag coefficient and the heat coefficient, heat flux coefficient. And here on the right-hand side is an example of a paper from BAO. But this also is very, very ongoing research at the moment still, because the way that we are generating sea spray is very difficult to model. It's very small scales, and we have a lot of parameterization on that. And it's very difficult to do measurement in such conditions. So difficult to have the ground truth, let's say. So to summarize, here, why we want to couple waves with atmosphere or ocean. So the wind wave interactions that are quite important are the fact that the waves obviously are generated by winds and influenced by them. In return, the waves will impact the surface roughness and modify the wind stress. So this is important both for the atmosphere, but also for the ocean, because it's influenced the amount of energy that is transmitted from the atmosphere to the ocean. They also modify the RC fluxes, momentum and heat fluxes, and eventually water fluxes, but more on the heat fluxes. And then we have seen that if the waves are going fast enough, they are not taking energy from the atmosphere, but giving back energy towards the atmosphere, which is quite important too, can be important too. And also, a wave can move part of the energy input to the ocean. So the atmosphere gives energy to grow the waves, and then the waves propagate and will break at a different area. And so the input of energy into the ocean will be in a different place, which is something to consider. On the ocean side, the wave current interaction, we have seen that waves are strongly influenced by currents, by water levels also, and by the bottom. They generate also currents and modify the water level at the coast and the bottom roughness at the coast. They enhance the upper ocean mixing, and they, through breaking also, they have strong impact on mixing, on sediment transport, etc. And I haven't shown so much about that, but one can imagine that obviously when waves arrive close to the sea ice, that they can also induce some force towards the sea ice, like they can break the sea ice, so change its shape, and also push it, so they will influence the ice sheet too. And finally, on the other hand, sea ice can also impact the dissipation of the waves and their propagation, of course. So now just a few words on how we can model waves and wave current coupling, because I've talked a bit about theory and processes, but now how do we do in practice? So as I said, waves, we have a large of scales to cover. So if we look at individual waves, we are on very small and short scales. And to go towards a wave climate, for example, at a global scale, you can imagine that it's quite a range of scales to model. So in the middle of that, we use the spectrum to reconcile, let's say, this individual wave motion and the wave climate and the impact on the global scale. And so we have two options depending on what we want to look at. So as I said, we can model each wave individually, which is a wave resolving models. At this moment, we need, with the model, to be high resolution enough to model each individual wave. And we need to account to a lot of processes. That is, obviously, typically, we are not hydrostatic anymore. This hypothesis that we do in general in the open ocean and for different typical processes, even at global or regional scale. With waves, we cannot consider that anymore if we want to really model waves, because obviously we have changed in the pressure associated to waves and stuff like that. So we definitely need to model non-hydrostatic features. And I think that tomorrow you will have some insight on that. But what I can say is with CROCO, we can do that. So if you want to look at really small scales, you can model individual waves and this evolution. And you can look at this nice paper from Patrick Marchesiolo, which illustrates that very nicely. Of course, here we are at scales that are really small. This is something important to remember. And then more generally, for larger scales, we use spectral wave modeling. So as I said, we consider the full spectrum, and I will show you this a bit further. And in the ocean model, what it implies is adding some wave, what we call the wave average terms, to the ocean model equations. So here I've put some typical model equation in CROCO, and you can see that instead of the usual velocity, we're using the Lagrangian velocity, which consider also the Stokes drift of the waves. Then we are considering also in the pressure gradient, the impact of the Bernoulli head pressure, which is pressure associated to waves. We are adding some terms of the Stokes drift also on the right-hand side. And finally, we have induced term for the dissipation and source terms, which is associated to wave forcing terms, so typically bottom streaming, braking acceleration, and diffusing term like wave enhanced bottom drag and mixing. So this is the way it's done in CROCO. And these terms, these various terms, Stokes drift, etc., Lagrangian velocities, Bernoulli head pressure are given from a spectral wave model, which can be, for example, a WaveWatch 3 model or another one. But here, just a word on how spectral wave model works. So we are, as I said before, considering the C state as a superimposition of various wave systems that we consider. And we are looking at this wave spectrum. And what is interesting here, you have a representation on the bottom of a typical wave spectrum. So it's given, you have azimuth, so a direction. And in the radial direction, you have a wavelength at this moment. And you can see that while waves are very irregular and very short, we can see that the wave spectrum have nice numerical properties, which is it's relatively regular and is varying quite slowly. So this is much more easier to model in a numerical model of the C state. And so, for example, in the WaveWatch model, we solve the equation of the evolution of this spectrum. So at each grid point, we solve the evolution of the spectrum. So in general, in CROCO, at a grid point, you have a dependency on X, Y, and Z, and time, obviously. But in a wave model, in a spectral wave model, you have a dependency on X and Y, and also a dependency on the direction of wave propagation and the frequency or period of wave propagation. So this is something to remember. It's you have all the time these variables that have two additional dimensions that are direction of propagation of waves and frequency of waves. And we are solving this equation, which is the conservation of action. Energy and action are related through this equation at the bottom. We use action because it's a more general invariant than the wave energy. But basically, it's conservation of wave energies that we solve. And in this equation of wave evolution, so we have the variation of the advection equation, the part of advection, which is solved through this various equations. So it's a hyperbolic equation with given well-known solution and methods. And then we have part of the source terms. And the source terms, this is where the parametrization stands. It includes generation by the wind, nonlinear evolution, so wave-wave interaction, let's say, dissipation due to breaking or to bottom friction, scattering, reflection, all the processes that we have talked about. And all this is parametrized. So this is also to note that there are a lot of parametrization in wave model, and it's really also evolving every day and every year. And it needs some expertise to set them well, let's say. So the accuracy of these spectral wave models depends on several things. First, obviously, forcing parameters, because it's strongly dependent on the wind quality that you prescribe, and also on the current, where you have strong impact of wave current interactions. It's very sensitive also to the bathymetry. But basically, what is generally the biggest source of error in forcing is associated to wind. And also there is a complex tuning, as I said, of parametrization and choice of parametrization that can be done in such models. And there is also usual model numerics uncertainties, so the order of the numerical schemes, etc. And generally about validation, you will see in many papers that generally the easiest thing to validate is a significant wave height, because we can measure that from altimetry. So this is quite well constrained, let's say, in wave models. But when you go towards the full spectrum, so the evolution of the wave system in terms of direction and frequency, we are talking about aspects that have been less and less validated, because it's more difficult to have this kind of observation. But let's just advertise that there are observations of the wave spectrum from buoys, obviously, but also from satellite data, but they are not very easy to use, and there are also some limitations that has to be known to use them. So just an illustration of what we have as output of wave models. So we can have typically full spectrum, as illustrated on the right-hand side. But also we can have what I've shown earlier was also 1D spectrum at the beginning of the presentation, which is actually integrated over all the direction. And we can also have typical bulk, what we say bulk or integrated parameters, which are the significant wave height. So it's the integral of the full spectrum, but also, for example, the mean period of the waves or the peak period of the wave. So this is the main wave system. And these are examples of pictures that you can have on windy, for example. And if you click on a given point, it can give you various what we name partition of the wave, so various wave systems that are computed by the wave model, like the wind C, so one part of the wave spectrum, the main swell partition, and the secondary swell partition, for example, with a given period, significant wave height, and frequency and wavelength eventually. Now, if we want to couple this wave model to an atmospheric or an ocean model, in our case, I will explain later that we use the Oasis coupler, but the idea is to give some parameters. So with the atmosphere, generally we exchange the roughness features, which is done through the Charnock parameters, or eventually the wave age. And to the ocean, what we can give is significant wave height, mean or peak period, direction, and also momentum fluxes computed from the wave model to the ocean model, Stokes transport, Bernoulli pressure, etc., all the variables that we have seen before. And in return, the ocean need to provide currents, water levels, and the atmosphere need to provide winds. So this is a typical way of coupling. So just this is my last slide for this presentation to let you know that so in CROCO, we can model wave directly. So what we have said, wave resolving thing. So for that, you need to be very, very high resolution, and you need to use the non-hydrostatic core of CROCO, but it's possible. Then, if you want to model like waves and coupled with the ocean in a larger area, you can couple with spectral wave modeling, typically WaveWatch, or actually wave models, including Oasis at the moment. And there is also an embedded wave module that is directly into CROCO, which is named the WKB module, which is actually a simple version of propagation wave propagation model, actually. So it's a monochromatic, so you have just one wave components, but you can propagate this wave. And for some nearshore application, it can be used also because it's very easy to set up. But in this case, you have many of the wave-induced terms like Stokes, drift, and bottom string and stuff like that are computed through parametrization and analytical formulation. And also there is no generation of new waves by the local wind. It's just propagation, and there is also the wave interaction. So this is something to remember, but that can be useful in a relatively simple nearshore configuration. So this is it for this part of ocean waves. I can take some questions.
Thank you very much, Swen. Questions, comments? Nothing there.
Okay, I don't know how much time we have left, Andres. Normally it's just 5 minutes.
Yeah, more or less. Yeah, we think we should be stopping, and then maybe in the practice session, then we will have the.
Maybe I can just take a few minutes to introduce the coupling with Oasis, because I had a presentation about that. So it's maybe I won't go into all the details, but it can be useful before the practice session to introduce that. I don't know. What do you think?
Yeah, okay. Yeah, please go ahead.
Okay, so well, normally it was something like a half-an-hour presentation, but I can skip some slides and anyway give them to the participant later so that they can find them. But just it's to introduce what we can do practically when we couple CROCO with Oasis and other models. So I think it can be useful to have an overview before practice.
Okay, great. Thanks.
I share my screen again. Is it okay? Can you see the screen? Yes?
Yeah, yes.
Okay, perfect. So it was just an introduction. I come back to this sketch that I have explained before. So what we do when we couple ocean waves and atmospheric model is to use these Oasis libraries that I will describe a bit to exchange all these variables that are computed by one model or the other in the time that we are computing them to have feedbacks of these different variables on the other models. So basically, Oasis is a library that is developed at Sarfax in France, in Toulouse. And it's a set of different libraries that provide some useful features. So there is the PSMI library, which is built for the exchange of variables and time interpolation, because the various models won't run at the same time step. There is a library that is MCT library for parallel exchanges, so for performance of this coupling interface. And there is the Spectral library, which is for grid interpolation, because we don't have, not always have the same grids for the various models, obviously. So the advantage of this Oasis library is that it's non-intrusive in the code. So it's quite just a few calls in a few routines of the model. So it's easy to implement and non-intrusive. And it doesn't request in-deep stuff in the code, so that if you change stuff in your code, generally you won't have anything to change in the coupling interface. So this is very useful. And it also allows us to couple a large variety of models. So CROCO has any model that has Oasis inside can be coupled to another model with Oasis. So typically in CROCO, NEMO, Surfx, Wave3, WRF, MesoNH, and probably other models, we have this Oasis interface, and we can couple this model together. So basically what Oasis does, and the way it's implemented, is there is an initialization phase, which is done to typically set up the communication between the models. There is also definitions of the grids, of the parallelization partitions, and of the variables to exchange. There is a step which is actually exchange fields, so put fields toward the coupler and get fields from the coupler. And then a finalization, which is the closure of communication, typically. And so just to show here what it implies in CROCO, for example, it's just that we had the usual CROCO code. We just had 6 new routines that actually do this initialization, definition, put, get, phase, and stuff like that. And just these 6 new routines are called in actually 3 scripts in the code. So the main for the initialization part and finalization. the get initial for the definition and the step, and that's all. So it's very non-intrusive. I have then the implementation in WaveWatch and WRF, but I will skip that. If people are interested, they can look at that. And typically, this is the sequence of exchange that we have when we couple. So this is an example with ocean and wave coupling, for example. So at the beginning, we have initialization files, so CROCO ini typically, and for WaveWatch, this restart for .wavewatch, for example. We need to have some files also to initialize the coupler. And then each model is running at its own time step. In this example, for example, for CROCO, it's 190 seconds. And for WaveWatch, it's 90 seconds. And at some point, which we name the coupling frequency, here it was 360 seconds, we decide to exchange fields between the two models. And Oasis performed that. So at each time step, Oasis just gets the values from one model, store them in its memory. And when it's time where we decided to exchange fields, it's provide fields to the other model. So this is quite simple. And Oasis is also able to perform some transformation of the fields that it's stored, typically time transformation that could be average, for example, so an average of a given window of time, or a grid transformation if the fields need to be put on another grid, the grid of the other model, for example. So this is the typical sequence. And at the end, it writes also a restart file for the coupler. The time transformations that can be done by Oasis are typically instantaneous, exchange instantaneous fields, so no time transformation, accumulation over time, average, and also give minimum and maximum value. In our case, honestly, we always use either instant or average fields, but for maybe specific application, it can be something else. And it also be able to perform some spatial interpolation, to be able to communicate between the grids. And there are all these transformations available in Oasis. So you can look at the Oasis manual for more detailed information. Then the way it works is that there is a name list named namcouple, which is a name list for Oasis specifically, in which we will specify all the fields that we want to couple. So we will give the number of fields, the name of the model executables. You can see here that the model executable are not the usual. For example, for CROCO, it's not just CROCO, it's CROCO X, because it was requested in the coding of Oasis that it was 6 characters. So typically, in the script, we move the name of the CROCO executable to CROCO X to be able to run Oasis with it. And then we have the time of the simulation that we want to perform, and some numbers for debug levels. And then we have a section where we will prescribe all the exchange fields. So these exchange fields will be prescribed one by one, and they have specific name that is related to Oasis and the way that Oasis is implemented in the models. So it's not the usual model name, but the name for Oasis. For example, here, for sea surface elevation in CROCO, the name for Oasis is CROCO SSH. And if the way that is prescribed in WaveWatch is WaveWatch is waiting for WaveWatch SSH. So we are just saying we will give CROCO SSH to WaveWatch, and then we are giving information on the coupling period. The digit before is not used. And then there is a digit that is the number of transformations that we will prescribe. You remember maybe time or space transformation. And here is the name of the restart file. And finally, exported here is a keyword to specify to Oasis if the fields are written at each exchange in a given file or just at the end. It's typically for debug. And then you have the following line is for this field specifically, it gives the grid. So the grid numbers in X and Y direction for CROCO first, and then for WaveWatch. Here it's the same because it was the same grid, but you can have different grids and then have different number of points for each grid. And there is also a little name here, Ocean T, WaveWatch T, which is the name of the grid for Oasis. And finally, this lag is the time step of the model that is sending the variable. So if you remember before, here it was 180 seconds for CROCO, so we put here 180 seconds, which is the CROCO time step. Here you can prescribe on the third line the type of grid that you are using. So here it's regional, but you can also have, for example, periodical grid. And in this case, it's a P keyword over there. And you can have overlapping points in this case of a periodical, for example, grid. Then it's a keyword to prescribe the transformation that will be performed. So here, Scripper, if you remember, is the name of the library for spatial interpolation. So it says, I want some spatial interpolation. And then the last line prescribes the type of transformations that we want actually. So here it was distributed weights in a long lat framework. So all this is detailed in the OASIS manual also, but it's just to give you an example. And for each variable that you want to exchange, you have to fill all these lines. So what you will have in your directory of run when you are using OASIS and coupling, you have some additional files that you need. So you need some restart files for the coupler. You have the namelist file for the coupler. And then, so this is input files. Once you have run your couple simulation, you will have some generated files. So you have some grid files that are automatically generated by OASIS and that gather all the grid settings that it needs to perform interpolation. You have grid interpolation files. So it's the weight of interpolation that OASIS have computed. So it's generated automatically too. And then you have some log files. There are several log files, and it's quite important to spot them because when you will have an issue in coupling, you will need to look at these files. And the summary of what you will do to set up a couple simulation is that. So it's quite important. It's not that easy, as Andres said earlier, but first, obviously, you need to get the various source code that you need. So CROCO, WRF, WaveWatch, whatever model you want to couple. You need to set up your environment. It's very important that you note that you have to have the same compiler and same libraries for all models. And this is important. And usually, first errors are related to that. You start something, there is an error, it's in general related to the environment. So we have prepared some scripts that you will be able to use in the practical activity that facilitates you to keep always the good environment with you. And then you need to compile. So you first need to compile OASIS before all of the other models, because then, as it is a library, you will link this library towards the other model. And then you will compile your other models in coupled mode. So that is linking OASIS library and also sometimes having some specific features in the model compilation. For example, in CROCO, and in all models, you need absolutely to be in MPI, otherwise it's not working. And also in CROCO, then you need to define, for example, ocean atmosphere coupling or ocean wave coupling, or both. But we also have something automatically set up by scripts in what we have in the coupling toolbox. Then you have to perform the pre-processing for your different models. So prepare your initial file, your boundary files, and surface files, etc. And then to define some stuff in the name list of your different models. So in the CROCO in, for example, or in the WRF name list, but also the OASIS name list, which is NumCouple. And you have to prepare the restart files for the coupler. Then you need to run. And as I said, OASIS is a library. So actually what we do is we launch both models together, but just the models. You don't launch the libraries linked into the model executable. So here is an example where we launch with MPI, WaveWatch, and CROCO at the same time, and on a given number of processors for each. And so both models have started to run, and at some point they are calling the library in OASIS that has stored some information, exchange this information between the models. And in the end, you have some output on log file to check. So I think I will skip some stuff then and just introduce to you the coupling toolbox that we have built, because as you can see, it's quite complicated. When you have to fill the name couple, your own name list, the restart files, etc., there are many sources of potential errors. And so we have built some scripts to automatically fill most of this stuff to avoid errors, user error, because it obviously happened. And so I will show you that, but in the slides that I will skip now, you can see that you have all these different steps from 1 to 7 detailed step by step. So later, if you want to go there, you can. Just, yeah, maybe some word on the architecture, because you will have similar one, I guess. In general, what we use is we have a config directory in which we run our configuration, and somewhere else, potentially the various model directories. And there are some scripts that are very useful, you will see. So you maybe already have used the createconfig.bash script, which helps you build this typical architecture for configuration. And this is useful also in this case. And you have the script that I told a bit earlier, which is the my-of-my-path. And this is important. You have to look at this script and check that it provides you the good environment for compilers and paths towards data that you will use. Normally, if you have used createconfig.bash with the left arrow keyword, I think on your case, you will have most of the stuff already correctly set up, but you have to check, and you have to source this my-of-my-path.sh before starting preparing your configuration and your work, your couple run. Then I skip some stuff. So this is Oasis compilation, but you will see that in the tutorial. This is the CROCO compilation also, you know it, WRF. This is a WRF preprocessing. This is a WaveWatch3 compilation also. So I skip all this, but you can look at that later. This also presentation is available on the CROCO website, so don't worry if I just skip that. This is also for preprocessing, and Fabien advertised earlier that there is good tutorial in the WRF website. This is definitely true, and I encourage you to go there. And we have also some tutorials available in the CROCO documentation, where we have some explanation also to set up WRF, and we have also provided some scripts to facilitate all the WRF preprocessing within the coupling toolbox. And so now let me just introduce the coupling toolbox, which is this. So as I said, we have the my-of-my-path in this coupling toolbox, which is useful, but we have also two other scripts that you will, two other files that you need to edit. So this is the my-name-list file, and this gather all the settings you need for the experiment. So which model are you using to use? What is the time stepping? What are the input files and stuff like that? And then there is my job file, which is the settings for the job, typically the date you want to run. If you want to run only one simulation or one simulation for each month with a restart in between or stuff like that. And normally, once you have filled these three scripts, you don't have to launch them. They will be launched automatically. You just have to launch submit job, and it does everything. So this is the theory. In practice, I hope it will work like that. But the submit job, what it does, it reads this definition, my-of-my-path, my-name-list, my job, and some common definitions. It also computes some, it reads some cal tools, so tools for calendar stuff to prescribe time settings. It creates a job. It submits the job towards the machine. And in this job, it gets the execution, the exe files, and eventually compile the ocean model if you ask for. It gets the forcing files for the ocean, the atmosphere, the wave model. It gets the initial and restart file. It edits the name list automatically, so you don't have to change them normally. It's always, the only thing that you have to set up is in my name list. It launches the run, And it manages also output. So it puts the output and restart in different directories so that you can use them for a following run, for example. And eventually it launches another job if you want to have kind of a loop for launching, for example, monthly jobs. So this is the idea of this toolbox. It's a lot of scripts, but actually I hope that it will facilitate your use of coupled runs. I think that I will stop there because we are running out of time, but you will see more in the tutorial in this afternoon.
Thank you very much, Swen. Yes, we will, when in the tutorial in the afternoon, we will review this presentation and see the code that is related to one of these. Yes. So I will stop the transmission.